Welcome back to Physics, Chemistry and Quantum Physics. So today we will be discussing about Maxwell's equations and relativistic electromagnetism. So this video has been divided into two parts. In the first part we will be discussing about Maxwell's equations of electromagnetic wave, and in the second part we will be discussing about the Lorentz force and the role of special relativity in electromagnetism. So let's jump right into it. The story of electromagnetism begins when Ørsted discovered that steady electric current moving through a wire creates a magnetic field, and later we got to know that changing electric field create magnetic field and changing magnetic fields create electric field. Now here comes James Clerk Maxwell as chorus physicist. He imagined that what if a charged particle was oscillating in free space, and if the particle is charged it has electric field around it, and if the charge is moving then it will create a magnetic field. But wait, the direction of motion is constantly changing, means the magnetic field is changing, which creates an electric field, and this cycle goes on creating so-called an electromagnetic wave. And Maxwell tried to calculate the speed of this electromagnetic wave, and he found its speed to be 1 divided by square root of epsilon naught multiplied by mu naught. Now epsilon naught is the constant of permittivity of free space and mu naught is the constant of permeability of free space. Now what is permittivity? Permittivity refers to the ability of a substance to store electrical energy in the presence of electric field, and permeability refers to the ability of a substance to support the formation of magnetic fields within it. The value of epsilon naught is 8.85 times 10 to the power negative 12 farads per meter, where farad is the SI unit of electrical capacitance, and mu naught, the value of mu naught is 4 pi times 10 to the power negative 7 Henry per meter, where Henry is the SI unit of inductance. So now let's discuss the value of that electromagnetic wave. The value of this 1 divided by square root of epsilon naught multiplied by mu naught is actually 299,792,458 meters per second, which is the speed of light. It means that light is an electromagnetic wave, and it was a groundbreaking discovery by James Clerk Maxwell. Now, to understand electromagnetism, we have four equations. These equations are known as the Maxwell equations of electromagnetic wave, and these basically describe electromagnetism. The first equation we have is known as the Gauss's law. The Gauss's law is basically used to describe the divergence of electric field. Now, what is divergence? Divergence basically refers to the outflowingness or the net outflowingness of an electric field, and it is denoted by the dot product of del operator and a vector quantity, which in this case is electric field. So, the divergence of electric field is equal to rho over epsilon naught, where rho is the charge density and epsilon naught is the constant of permittivity of free space. In its integral form, this equation looks something like this, and this basically describes the closed surface integral of electric field, which we can say it is the electric flux, and which is equal to the charge enclosed divided by the constant of permittivity of free space epsilon naught. So the divergence of electric field is equal to rho over epsilon naught, and by this we can say that charges like positive and negative charges can exist freely in space. The next equation we have is known as the Gauss's law for magnetism, and it basically describes the divergence of magnetic field or the total outflowingness of magnetic field. Now the divergence of magnetic field is equal to 0. It means that there is no net outflowingness. So what does it tell us? It basically tells us that there can be no monopoles in the universe. Means each and every single magnet in our universe should have a north and a south pole, where the magnetic field lines emerge from north side and goes to the south side, and there can be no monopoles in the universe. Every single magnet has to have a north pole and a south pole. The Gauss's law of magnetism in its integral form looks something like this, and it basically describes the closed surface integral of magnetic field, which is equal to 0. Means there is no net outflowingness of magnetic field. And the third equation we have is known as the Faraday's equation, the Faraday's law of inductance. And this equation is one of the most important equations in electromagnetism, because 90% of electronic devices at your home work on this particular principle. And let's see what it tells us. So it basically tells us the curl of electric field. Now what is curl? Curl is basically described as swirling, or we can say rotation, how much a vector rotates, and it is denoted by the cross product with the del operator. So if we have del operator with a cross product, then it's known as curl. And the curl of electric field is equal to negative the derivative of magnetic field with respect to time. Now, it tells us that an electric field can be created by changing magnetic field with respect to time. So, if we have a changing magnetic field with respect to time, it will create an electric field. But what is the use of that negative symbol? That negative symbol basically tells us that the electric field which is created through the magnetic field, through the changing magnetic field, will be opposing in nature. Now, in its integral form, the Faraday's equation looks something like this. Now, this tells us that the line integral of electric field along the closed path is equal to negative the rate of change of magnetic flux with respect to time. So, if we have a changing magnetic flux, we will have an electric field. Now what this equation tells us is that imagine we have a ring of a conductive material and we have a magnet. If we move that magnet back and forth through that ring, what will happen is that an electric current will be induced in it because of changing magnetic flux, and that induced electric current is known as eddy currents. So what are eddy currents? Eddy currents are basically induced currents that occur due to changing magnetic flux. And this eddy current principle is explained by the Faraday's law. Now let's move to the fourth equation. The fourth equation is the Ampere's law. In its differential form, the Ampere's law tells us that the curl of magnetic field is equal to mu naught multiplied by the electric current plus mu naught multiplied by epsilon naught multiplied by the rate of change of magnetic field with respect to time. So what does it tells us? Basically, we can say that a magnetic field can be created in two ways, in one of two ways. The first way to create a magnetic field is the first part of the equation, which is mu naught multiplied by the electric current. So if we have an electric current, a steady electric current, it will create a magnetic field around it. And the other way to create a magnetic field is the second part of the equation, which is the rate of change of electric field with respect to time. So if we have a changing electric field, we will have a magnetic field. Or if we have a steady electric current, then also we are going to have a magnetic field. So there are two ways to create magnetic field. One with electric current, and the other one is by using a changing electric field. Now, Ampere's law in its integral form looks something like this. This basically tells us the line integral of magnetic field along a closed path, and this is equal to mu naught multiplied by the charge by the electric current enclosed plus the mu naught multiplied by epsilon naught multiplied by the rate of change of electric flux with respect to time. Now, for a second, let's move to our explanation of eddy currents. We discussed that if we have a magnet and we moved it back and forth through a ring made up of a conductive material, then what will happen? That an electric current will be induced in it, which we call as eddy currents. But we learned that from the Ampere's law that electric current will create magnetic field. It means that eddy current is going to create its own magnetic field, and that magnetic field will be opposing in nature. So, for an example, if we drop magnets through a copper pipe, then what will happen? The magnet will slow down because the because the moving magnet will create eddy currents, and those eddy currents will create their own magnetic field which will oppose the motion of that magnet, which explains the Lenz's law. The Lenz's law is this only, that if we drop a magnet through a copper pipe or an aluminum pipe, then what happens, that the magnet slows down due to the Lenz's law. And we can describe this Lenz's law and eddy currents using the principles of Maxwell's equations. Now, I hope that the concept of Maxwell's equations are very clear to you all, and that is the reason let's move to the next part of this video, in which we will be discussing about the Lorentz force. Well, you know, Maxwell's equation don't describe the whole story of electromagnetism. We need one more equation, one additional feature. Now, Maxwell's equation don't really describe that how a charged particle is affected in an electric or magnetic field. It is the Lorentz force equation that really describes that how a charged particle is going to be affected in an electric or a magnetic field. The Lorentz force equation basically looks something like this, and which describes the force that acts on a charged particle, which is equal to QE plus QVB, where Q is the charge of the particle and V is the velocity, B is the magnetic field, and E is the electric field. It means that if we have a charged particle, in an electric field, which is the first part of the equation, charged particle in an electric field, there will be a force acting on it. And if we have a charged particle which is moving in a magnetic field, then there will be a force acting on it. There will be a force in two different ways. If we have a charged particle in an electric field, or if we have a moving charged particle in a magnetic field. Now, you know, what is the reason? It is one of the most basic questions that arise into minds of physicists, that what is the basic reason behind why electrostatic force creates magnetic force? Like how changing electric fields are creating magnetic field. What is the reason behind this? This is basically explained by so-called special relativity. We already have a series on special relativity where we have discussed about it in a very detailed manner. So if you want, you can check it out. And the thing is that length contraction effect actually describes that why changing electric field can create a magnetic field, or why electric current will create a magnetic field around it. So let's discuss about it. Let's imagine that we have a wire and it has negative as well as positive charges, and we also have a positive charge which is kept beside the wire, and now nothing is going to happen. And if we have an electric current in that wire, it means that we have a moving electrons, still nothing is going to happen. But if that positive charge which is kept beside the wire starts moving along with those electrons, what is going to happen? That it will be repelled from the wire. Now, why is it so? If we observe this phenomena from our perspective, we can say that the charged particle, the positive charged particle, was repelled by the wire due to a magnetic force. What happened? That moving electrons created their magnetic field, and the moving charge created its own magnetic field. The magnetic field was repelled by another magnetic field. Everything is normal. But wait a second. If we observe the same phenomena from the perspective of that positive charge which is moving along with those electrons, from its frame of reference, we can say that electrons are stationary because it is moving along with those electrons, and the rest positive charges, they are moving in the opposite direction of that particular positively charged particle. So we know that length contraction effect happens when we are moving close to the speed of light. Now, what is length contraction? In our previous video, we have discussed about it. So if you are interested, you can check it out. Basically, length contraction is a phenomena of special relativity, in which if we move close to the speed of light, what happens that the path through which we are moving contracts, and we have to travel less distance. So in this thing also the same phenomena is going on, the length contraction effect. So what happens that as the positive charges are moving in the opposite direction in the frame of reference of the other positive charge, the distance between those positive charges have been contracted, and there is a net positive charge in that wire with respect to that particular positive charge which is kept beside it. So in the frame of reference of that positive charge, we can say that the wire is positively charged, and positive charge repels another positive charge. We know it, and this is due to an electric force. So in our perspective, it was a magnetic force that made the positive charge repel from the wire. But in the frame of reference of that positive charge, it was the electric force. So what does this tell us? This basically tells us that electric force and magnetic force, they are actually the same thing. Electric force may be a magnetic force observed from different perspective, and a magnetic force may be an electric force observed from different perspective. So magnetic force and electric force, they both are just heads and tails of the same coin. If we view it from another perspective, it may be an electric force. If we view it from another perspective, it may be a magnetic force. So I hope that the point that I am trying to make is very clear to you all. And if you enjoyed today's video, then don't forget to like, share and subscribe to our channel. And thanks for watching. We'll meet in the next video, my friends.